Hello, everybody. I'm Henry Foucault, Junior Boateng from Withers Ravenel, working in the North Carolina office. And today I'll be presenting on the topic titled The Odd Couple, Sewer Overflow Modeling and the Similarities Between Pittsburgh, Pennsylvania, and North Carolina. So I will start with a brief introduction of what sewers and sewer model entails. Then I'll provide a brief background on the sewer systems we will be looking at and what the model development is about. The calibration and comparison will be at the latter end of this presentation, and hopefully we will take some few conclusions home with us. Sewer systems are a network of pipes, pumping stations, and appurtenances that convey excess water, be it storm or wastewater, from collection points to treatment or outfalls. Today, we will be focusing more on sanitary sewers and combined sewers. Sanitary sewers are basically sewer systems that convey only wastewater, whilst combined sewers carry runoff and sewage water. These systems serve domestic, commercial, and industrial purposes. North Carolina only uses sanitary sewers in its sewer system. Pennsylvania have both sanitary and combined sewers in their system. Both systems have had their fair share of sewer overflows, and sewer overflows normally occurs as a result of flow exceeding these sewer systems, mostly during heavy rainfalls. So one may ask, what has been the impact of climate change on these systems? The only thing I can say for certain is that these highly variable rainfall patterns and intensities caused by climate change have done nothing to help sewer overflows. Even the intensity, duration, frequency curves used to divide design storms were done before 15-minute rainfall data was available. And a lot about our climate has changed since then, not to even talk about the effect of the aging infrastructure, which is one major contributing factor to sewer overflows. It is very alarming, as EPA estimates about 23,000 sanitary sewer overflows every year. Therefore, it is important to know where the shortcomings are in our system. And hydraulic models seek to provide this answer for us. They help us to understand our systems, how it operates, where hydraulic constrictions exist, and what can be done to make it better. We will head on and talk about the various sewer systems under review today. We are going to start with a sewer system in North Carolina located in the city of Sanford. Of course, as I said earlier, North Carolina has only sanitary sewers to carry wastewater, so we will be looking at one. This particular sewer system serves over 25,000 customers, be it domestic, commercial, or industrial. It consists of mostly gravity mains, a couple of lift stations, and force mains to move water where ground elevation is not of help or where additional force is needed. One issue the city has been grappling with is sewer overflows. With the city looking at accommodating future growth, it is important to see how these problems come about and how to even solve them before future growth can even be considered. In theory, sanitary sewers should not be directly impacted at all by flooding, but it's only supposed to carry wastewater. However, in practice, we have seen this not to be the case. Most of the systems were built in the 1800s and early 1900s, where hydraulic considerations were rarely talked about. Contours were not even available, and during these times, the predominant material in sewer construction was vitrified clay pipes. And we have seen numerous rehabilitation projects go on and on for decades. However, most of these systems are still made of clay. Per North Carolina state laws, every sanitary overflow exceeding 1,000 gallons are supposed to be reported within 24 hours. It is very overwhelming to know that in a 2020 survey, the North Carolina Department of Environmental Quality recorded about 16 million gallons of untreated sewage spilled into our waterways just during a 2.5-month period. That's between May 17th to July 30th. The map on the screen shows the city's sanitary collection. It consists of 9 lift stations distributed across the system and significant gravity sewers ranging from 6 to 36 inches in diameter, and also a wastewater treatment plant north of the system. In Pennsylvania, we will be looking at the city of Duquesne's combined sewer system. It serves about 6,000 customers, which is only a fraction of the city of Sanford. It was actually built in 1959 to basically solve the problem of open discharge of untreated sewage into rivers, which was primarily destroying aquatic lives and polluting the river. So they basically said they only want to treat base water flow. So when it rains, anything above the base flow skips over to rivers. And they used overflow structures like diversion chambers and weirs to divert this excess flow. Fast forward a couple of decades, a newer sanitary technology becomes available. Cities are now opting for sanitary systems which are separate, and combined systems have now become inferior. However, it is a close to impossible task to change the city's sewer system altogether. The sewer system is under the Allegheny County Sanitary Authority, and through research, there's an estimated amount of 9 to 10 billion gallons of untreated wastewater that runs into rivers every year, and that should be a concern to everybody. Most of these combined sewer systems are bounded by the 85 EPA capture rule, which simply means that 85% of wastewater collected are supposed to be treated before discharge. However, rainfall intensities increasing and increasing with time has made this feat very, very difficult. On our screen is the city of Duquesne's combined sewer system, which shows the different sizes in pipes. It only consists of gravity mains, meaning there are no lift or pump stations, and the size ranges from 6 inches to as big as 72 inches. There are also 4 diversion chambers, and hence resulting in 4 outfalls, 2 being overland and 2 into the Monongahela River. And finally, a waste treatment plant. So for our model development, we will start to seek to juxtapose these systems briefly and understand the physical and operational data that will be used to build our models. These two systems are quite similar and dissimilar depending on what you are looking at. The clear-cut difference will be the presence of lift stations and the absence of overflow structures in sanitary systems. So this table shows the different types of pipes, manholes, wet wells, diversion chambers, and other operational data that will be needed to set up a model. Before we go ahead to develop a model, one thing we are supposed to focus on is the source of our data. Ideally, a modeler is supposed to be excited, to have all your data points surveyed and digitized before modeling. However, we can all attest to the fact that this is not the case. And creating data flags helps you in the long run, especially when you are going through calibration and you are wondering why a particular entry or elevation seems off. Although it might seem to be of no consequence, it is very important. Data flags are not limited to the table provided, but depends on the number of sources your data will be coming from. I would like to speak briefly on flow meter data for a short while and why everything must not be taken at face value. We can all look at meter 61, which is the meter on the right before the treatment plant, and 303 further upstream. Ideally, flows are supposed to be increasing as we go downstream. However, looking at the flow time series, this is not the case. The 303 represents purple and the 61 represents green. In most occasions, we can see the 303 being way higher than 61. So if you don't pay attention to these particular things, you might be able to start your modeling on the wrong foot. For the city of Duquesne, the flow inconsistency was by an egg-shaped pipe. So the depth in an egg-shaped pipe will generally be higher when you are comparing it to a circular pipe. So it made these flow meters to over-exaggerate the flow that was going through these pipes. So these are simple things that you would have to check when you're looking at flow meter data. For our model calibration, it consists of wet weather and dry weather. So our dry weather simply consists of periods where there are no rainfall, and our wet weather consists of periods where there are rainfall. I reckon that we are modeling sanitary sewer systems for the city of Sanford, so why should we worry about rainfall, as it's not even supposed to carry runoff? However, during wet weather events, there is something called rainfall-derived infiltration and inflow that contributes water into these sewer systems. There are many reasons why there are defects, and one is through pipe joints, service laterals, and even broken lids of manholes. For combined sewers, inflow of water is to be expected, but for sanitary sewers, we can see that Sanford's time series is changing every time there is a significant rainfall event. So we are supposed to take particular notice of these changes in flows to be able to curb sewer overflow. So we are going to talk a little bit about dry weather. Dry weather is basically a depiction of the average sanitary usage of the system, and we will not be focusing a lot on dry weather, as we would want to make good use of our time. So if anyone has any other question about dry weather, they can please let me know about this in a Q&A session. Then now we'll move on to the bigger piece of the pie, that is the wet weather events. So wet weather events are selected based on rain gauge recordings and the sewer system's responses to significant storm events. To calibrate the sewer system to wet events, we must figure out the RDII, that is the water that's entering the system through rainfall. So just like watersheds for storm systems, sewer sheds must also be created for these sewer systems. The sewer shed was developed by calculating 50 feet on both sides of every gravity sewer. The assumption is based on several laterals from houses being 50 feet to a gravity main. This number can be revised based on the modeler's own discretion. The method that was used for this calibration was the RTK method. And this was used to estimate the RDII that was going into the sewers. The RTK method basically signifies the R, the fraction of rainfall going into, T, the time it takes for the hydrograph to peak, and K, the time it takes for the peak to recede. Initially, there were to and fro calculations that were used to estimate these parameters. However, with the development of the sensitivity-based tuning calibration, that's the SRTC in Icwmm, this has become way less easier. The other thing in the combined system is that they have measurements to actually know what is going through these overflow structures, whereas in the sanitary, it overflows and is just lost. You don't know how much water or wastewater that your sanitary system is being flooded by. And that is a very big disadvantage to the sanitary system, considering it is supposed to be the newer system. So these are the modeling results for both sewer systems. We can clearly see both systems' responses to rainfall. These are proportions of the system where it overpredicts or underpredicts. It is necessary to note that the calibration inefficiencies may be due to a myriad of reasons, one being meter malfunctioning, the other being sources of error, especially from the pump efficiency of these pumps, as we all know that as time goes by, the pump efficiency recedes. The other thing is lacking a comprehensive pipe inventory to properly proportion roughness coefficients depending on not only the material type but also the date of installation. And finally, being able to interpolate less. So the more you interpolate, the less accurate your model would be. So although it is good to look at a hydrograph to see where the calibration is accurate, scatter plots of the observed versus the calibrated provides the best understanding of calibration efforts. It is necessary to reduce your square errors to be able to achieve accuracy. And it's important to note that not all rainfall events are supposed to be wet weather events. Rather, the quality of the observed data should also be taken into consideration. And most importantly, we should all encourage the multi-event modeling. So this represents a 10-year storm analysis performed on the City of Duquesne's combined system. We can see lots of flooding with some exceeding about 30 gallons. So this model is supposed to serve as a guide for the city to size up pipes or where they would install overflow structures to help reduce flooding. To make this fair, we also run a 10-year storm analysis for the city of Sanford. The flooding here is relatively higher than the city of Duquesne, although we must also take into consideration the different design storms. However, the flooding in sanitary sewers is still highly undesirable, especially when we have flooding exceeding over 50,000 gallons. So this model is also supposed to help the city to better their system. We are going to briefly compare these different systems and we will understand why they are a so-called odd couple. So when you take a look at the R value, which is the fraction of rainfall entering a collection system for both cities, for Sanford, there are portions where it is usually high. As much as 25% of rainfall enters the sanitary systems. Sanford's sanitary sewer is virtually a combined sewer, to be honest. The difference between these two is that Duquesne has an overflow structure that can expel excess water to rivers. If you look at the city of Sanford, by law, sanitary systems are not supposed to have overflow structures. So you therefore see lots of SSOs in Sanford than in Duquesne. We are going to wrap up this with a few conclusions. The conclusions are in three parts. The first one is the importance of a calibrated model. Calibrated models help us understand our system and get a good feel for where RDI are worst. And this is a decision maker in rehabilitation efforts. It also advises the cities to understand where there are critical elements in their system so that they will be able to know where to spend their money on. The next thing I will talk about will be about best modeling practices. We all know that I've spoken a lot about data flags. Another important thing we should look at is data analysis, getting to understand where your data inconsistencies are and reaching out to the interested parties to seek clarification. The next thing is going to be about flow monitoring. Make sure you check your flow monitoring data critically. As I said earlier, not everything you see is actually happening. And the last point is always seek to get more data as possible, whether it's pump curves, pump configurations, whatever you can get. Just try to get as much as you can get. However, if you don't have a lot, you can still be able to do more or less. All you have to do is just use assumptions based on industry practices. Then it leads us to our final point. How can we make sanitary sewers function less like combined sewers? The first thing is creating a GIS database for the city, where it's not just about positional data, rather entries like rim and invert levels for elevations, pipe sizes, and materials for pipes. The other thing will be replacing old worn-out pipes with newer ones of better material. The next one would also be the modeler being able to communicate the particular places where meter placement will be helpful, because metering for modeling is different from metering in other aspects of engineering. The final thing we are going to talk about is how the city can use their land growth projections to better their systems. So all things being equal, the city should be able to change particular areas where they had thought of maybe setting up industrial sites. They can also think of changing those industrial sites to residential areas where flow would be reduced. So those are the few things that you can do to make your sanitary system act less like a combined sewer. Thank you guys very much. I'll be taking questions after.